And anyone who's got a halfway decent camera, I don't know, can you do it?
You can.
Yeah, okay. They got Milky Way and just beautiful pictures, and I think John will be willing to have a bunch of us. I want to go. Leonard, you're gonna let me go this time.
I can't go.
You might
Lovely.
say, oh, stay home. But anyway, yeah, so that may be a whole nother offshoot of our group is
It's a good
to
spot.
get people out
Is
with
it okay?
cameras and getting some of these great pictures.
I get too excited.
Before it gets too cold and snowy. Anyway, okay, so. I'm gonna
I'll move it
do
then.
this pretty quick. Our next meeting is November 3rd. You'll get your Mountain Messenger, maybe a day or two after November 1st.
Thanks, I appreciate it.
Or October 1st, because I'm helping Annette with that, and she has some previous commitments, so I think we're gonna put it together on the 30th, so you probably get it the 2nd. So on November 30th, we have Dr. Dan Durda, who's going to talk about his research in the meteor crater in Arizona. Do you all know about the meteor crater? Yeah, okay. And also, a few days after this talk, he'll be flying to Florida and then going up in one of the airplanes that creates microgravity and doing experiments there. So he'll talk about some of his previous trips doing that and what he's doing in research. He's an asteroid expert, works at Southwest Research Institute in Boulder. And I'm sure you'll enjoy it. He was here about 3 years ago and just did one on his space art. He's a space artist and also a bird enthusiast, and he's quite a good. And he applied to be an astronaut, but he was in the finals, but really. Just want to say, if you haven't given a talk, you're free for life here. We just asked a $5 donation to cover the renting the hall, a few other expenses. We also have some Skywatchers stickers, more stickers. If you want some of those, that's another thing that covers. And then, let's see. So if there's a little bit of wine back there, not sure how long it's going to last, but if you want anything else, coffee, tea, we didn't make it, but we can make that for you if you want. Bathrooms are in the back if you've never been here before. And just want to mention our Facebook page. It's just Coal Creek Canyon Skywatchers, and Carolyn Collins-Peterson could be here tonight, but she updates it with some things to see in the night sky and our meetings, and the group picture, which Dave will do a group picture at the end. Okay, we'll all come up here and do that. Also, the Wonderview gift shop. Sandra here works there, and she's got a number of space books, maybe Amanda's book.
I just
Did
picked
you
up
talk-
information on that and was reading it.
Okay, so
Yeah.
maybe, and they cover, or they carry Leonard's Mars book and John's star cards and
I have some in the back.
and he has some here too. Dave Schammel has some of his cards on that little open there, spread out, that he's done a beautiful shots of the moon and lots of different things. And then he's got some new ones of hummingbirds, he said, he got these
Not
back
for
in.
free.
Not for free, they're what, $5 each? Amanda has her book here, both in hardback and paperback, and I guess the paperback is $15. How much is the hardback?
25.
25, okay. And I'm trying to get through all this. Okay, so want to thank Park and Rec, who's our sponsors. And yeah, and yeah. What? And we've got. Yeah. Oh, so on the back table, we have a bunch of things we got from the Space Science Institute in Boulder that we had at the booth, and we've got a lot of Cassini little cards that tell about it, and flyers and things. So please pick some of those up. We've got a lot of them
For free.
for free. Then I don't know if we've got enough of these, but if not, let me know if you don't get one. These are the September sky calendar with John's Coal Creek Canyon sky chart on the back. And then these are the October ones, and he's going to do this is another sky map on top of this, but he's going to do the one for Coal Creek Canyon that has when the space station flies over. You can do those, on October 1st.
Yes, October 1st, they'll be on the website.
Okay, and then, I'm not sure how all of you who are local here feel about this, but, I wanted to pass out also information on the Scott Roast Dam Reservoir, project. I've got this yard sign to show you here, and the reason why this is so important, and I can pull this in for us, is, that if they do this, and if you don't know much about it, definitely, go to the website, you can find out more, but, if they do this for 7 years, they will have big lights on the top of the dam, and they will interfere with our ability to see, we'll still see the planets and the moon, but, it will interfere with our ability to see the stars. And, so that's how I'm tying this, advertisement in. You can get a yard sign on their website if you want, that looks like this, and you probably, most of you have probably, how many of you have seen these around the canyon already? Probably, yeah, some of you. So, I think that's in, okay, the autumnal equinox officially is today, and we're celebrating this here tonight. And David, that's at 3 minutes to
7:54.
7:54 is when that actually happens, where it's equal day and night at that moment.
That's a good explanation.
Okay. And come back for another time when David Elmore will give us another talk. He gave us one before, and he'll tell you more. So the International Space Station flies over at 8:07. So Amanda has agreed that it's okay with her if we'll let her know about 8:05. And it's clear, so we should be able to see it. Should be coming, I think, from about there to here. It's pretty high in the sky, and it's very bright.
5 minutes.
And yeah, it's about 5 minutes. With the trees, we might see 3 or 4 minutes. But we'll just go out there, check it out, and come back and hear the rest of her talk. Amanda said she's okay with you asking questions during her talk. And thank you for coming. And
Let me do a few little things that are happening right now. As we sit here, we hope we can now. These people are very happy. This is the Japanese Space Agency support crew for an asteroid mission that is just doing already some spectacular things. They're very happy because their spacecraft, the Hayabusa 2, has pulled up to this this particular asteroid, and here's the kind of images they're getting. And so this is nothing when you see them coming. This spacecraft is multifaceted. It actually is going to cheat sheet. Launched in December 2014. Okay, it's going to pick up samples from the asteroid and bring them back to Earth in a re-entry capsule and come back into Earth. But here's the shadow of the spacecraft above the asteroid just a few days ago. And just as I left home, the spacecraft deposited 2 mini robots that roll around, that will actually hop on the asteroid. They were successfully ejected. They're both down on the surface of the asteroid. And sort of an artist concept of these things floating down on top of the asteroid. Here's the first picture from the one of the robots that actually, right in the middle of hopping from one place to another. This just came in like a couple hours ago. So it's pretty cool. It's right now, and amazing technology. The United States has another asteroid mission en route, OSIRIS-REx, that's in a few. Amanda, we talked about this. Where is she? Yeah. Okay, so the OSIRIS-REx, we're probably gonna be seeing stuff coming from that mission
In October.
in October, so this is a big year. Okay, dust storm on Mars. We talked about this last time. This has plagued the solar-powered Opportunity rover on Mars, and in fact, as of this morning, not a peep from Opportunity. We may have lost this rover, we don't know. They're sending signals, trying to reactivate it. This is Opportunity before it was launched, but it's the dust, on top of the solar panels. This thing's been going on for many years, but it's still got a long life if it comes back online. One other worrisome thing that people have not picked up on very much is that Curiosity has had some kind of software glitch, and it's pretty much mired in some mental breakdown on Mars. They're trying to fix it, but it's been many, many days now that this particular nuclear-powered rover on Mars has not been active. So we'll see. I think everybody's hoping for the best. They got the best engineers at JPL and elsewhere working on solving these problems. So be aware that we may have 2 inactive rovers on Mars right now. And maybe they're gone, maybe they're not. We'll find out. One cool story that just happened. Elon Musk. How many people have the Tesla car? Anyway.
Or waiting.
Yeah, my other car's a Tesla. Anyway, he's also the SpaceX rocketeer, and he is fashioning the big, what they call the BFR, which stands for, in some people's terminology, the Big Falcon Rocket. Anyway, he's really come up with a plan to launch this guy with a bunch of artists around the moon, a circumlunar flight. It's not going to happen anytime soon. Elon Musk has got a lot of rocket work to do, but the promise is there to do something on a private scale that only Apollo 8, when we first, navigated the moon, and other missions after Apollo. But anyway, this is kind of a scale drawing of his spaceship that Elon Musk is building. But it's kind of cool. It may go by unnoticed by a lot of people, but October 1st is sort of a historic period of time for NASA. As a space agency for the American government, civil space agency. October 1st is the anniversary of NASA, and so they're getting ready. They're going to do 6 decades of all the things they've achieved. You got to remember where NASA came from. It was pretty much fear. It was this thing.
Yeah.
This came in 1957, October 4th. Sputnik 1 rattled everybody. What are they doing with an artificial satellite? That was the first artificial satellite on the planet Earth. So this guy, Eisenhower, took note of this spectacular achievement, and they created out of this group, let me back up here, sorry. We have already in tow this group, National Advisory Committee for Aeronautics, NACA. This is a picture from their first meeting. This is like, these all guys look like they flew in the Wright brother plane. But, that was the beginning of aeronautics research for the country. And out of that agency, they took the best of things that were going to happen, and they created NASA. Okay, one last thing I want to talk about that I'm really kind of excited about, because I'm a big orbital debris problem guy. I think we have a real issue. A lot of people know that orbital debris has become something that we have to deal with and cope with. It's only getting worse. And there's been lots of ideas about how to decrease the amount of debris around the Earth. Okay, for the first time, a CubeSat was deployed from the International Space Station just not too long ago, and it had a net inside of it. And they deployed the net to capture another CubeSat that this larger spacecraft deployed, and to show that a net could actually capture one of these things. Well, they did it. And just a few days ago, they unleashed this thing, and the net went out and captured a spacecraft that had previously launched. And so they've come up with a concept, at least one idea, of how to capture maybe an uncontrolled satellite that's in hazardous mode around the Earth that could affect other satellites. So that's the beginning, but there's so much more to come. That's only one part of the story. Lots of debris, much of it very small, down to paint chips. And when you run into a paint chip going 17,000 miles an hour, it can cause a problem too. So we'll see where this goes, but at least for the first time, we've had an active in-space demonstration of a capability that for larger spacecraft, we might be able to snare them and get them out of the way from other spacecraft. So it's a good beginning. I threw this in because Steve's here, right? Steve worked with the Sierra Nevada Corporation. Well, they shrunk the spacecraft to be a toy. This is now available as a little matching toy. And this is built down in near Boulder. And so the spaceship, the Dream Chaser it's called, is available for purchase for Christmas.
From Mattel.
From Mattel.
Are you telling us your wish list for Christmas?
Anyway, I think that's it. Anyway, thanks a lot. Just a few little things over there. Okay, where are we doing now?
It's me.
John's next.
Pardon us for a second while we switch everything up. Yeah.
No, I came here for a couple of, maybe an hour after yoga.
Destroyed
And I tried to recreate, for those of you who were here last July, what happened to the screen there, and I couldn't do it. So I think that's a good sign, maybe. But I think we know how to solve it.
Pay John extra money.
Oh, yeah. You know, all about cabling, right? Come on. There it is. Yay. Step on the cable. You don't want to see me fall. So every month, I like to give the thing that Leonard gives. Talking about astronomy news, we haven't seen each other for 10 weeks, and I have to tell you, there's way too much to talk about, so I picked a few things out. But they've only been in the past few months, or past few weeks, I mean. So, I have to get my notes out because some of these things, please ask questions. If I don't know it, then our handy little tricorders will look up the I only threw this in because Dave and I work with the National Solar Observatory, and I don't know if you've heard, but it was closed the past couple weeks or the past 10 days.
Yeah, what's going on?
Do you want the real answer? Unfortunately, it was the speculate. I'll go with the speculation first. Speculation. There is an antenna on top that supposedly is pointing down to White Sands, and the Chinese hacked into it and are spying. That's false. This is the Dunn Solar Telescope, and it is as deep in the ground as it is tall. 6 stories tall, 6 stories down in the ground. A great engineering marvel. It was built back in the 50s and 60s. Anyway, it's got a lot of stuff. There's science going on down below, but since Roswell, New Mexico is 200 kilometers away, just a short trip by UFO to Roswell, New Mexico, there must be aliens down there. False. It turns out to be a little more sick than that. We have a janitor that's not part of the NSO staff. Now, the Dunn Solar Telescope was taken over by the National Science Foundation and is being transitioned to New Mexico State University. It'll still do science, and it was still doing science. we evacuated the whole area, including all the buildings, there's some residences and a post office up there. We evacuated it because a janitor that is contracted with the National Solar Observatory or with the New Mexico State University made some threats. And the FBI came. But he made threats because he was doing not so good things with our wireless network, like looking at, according to the court documents, he had child porn. So unfortunately, it's sick and mundane. But he's been taken care of, and he's in custody, I've heard the last. So unfortunately, everything on Popular Mechanics, Washington Post, everybody was talking about the alien conspiracy, so that was not what was going on. It turned out it's back up. We brought everybody back Thursday, and it started to do science again. We've started the schedule up on it, so it's still doing science. So I just want to let you know, since you guys probably heard about that, it was nothing as exciting as it could be. So we sat here when
Wrong!
Stern.
Wrong!
Down in the back, down in the back. Here. So back in 2006, the IAU made some new definition on what a planet is. It has to clear its orbit. It needs to be circular inside, so it has gravity. Spherical orbit, doesn't orbit other bodies, that kind of thing. But this new paper came out in Icarus, I guess, according to my research. Anyway, it came out in Icarus. Alan Stern was part of this paper, but this guy,
Metzger.
what was that? Metzger came out, and he's done some other things too. This is not his first go-around with Pluto as a planet. But he claims that, they went back and looked at the papers over the past 200 years, and it turns out that a lot of scientists don't use the word planet correctly. In fact, in the past couple of years, people have even used planet in papers to describe Titan and Europa, which are moons of Jupiter, or Saturn and Jupiter respectively. And so he says, this is kind of a wishy-washy definition. It needs to be better. Anyway.
Here's all that matters. How many planets do you want to memorize? You can memorize 8 or you can memorize 50. Okay? Your choice.
So,
Pluto's easy because the Disney characters named after it. I already got that one down.
It's because there's so many planets out there as big as Pluto and like Pluto. You have to memorize them all.
and I have to admit, I'm kind of in that camp too. It's when,
Just reporting the news, right?
no, but I am actually, after listening to Mike Brown talk, or, Neil deGrasse Tyson would like to claim that he made a dwarf planet, but it was really Mike Brown and his team when they found Sedna and those other ones.
Everybody loves Pluto. It's super cool. I love Pluto. It's a dwarf planet. That's what it's called.
Dwarf icy
Dwarf
ball.
planets are cool too.
Yeah, I know. It's
Yeah,
still-
totally.
My deal is it's still a planet. Anyway, moving on. Done with you in the back. So Proxima Centauri, I don't know if you knew, 2016, the scientists at ESO, the astronomers there, they found a planet that's very close. Proxima Centauri is less than 4 light years away. It's part of the Alpha Centauri system. There are 3 suns in that system. One of these there's this Proxima Centauri B, or Proxima B, is what they call it. And it, according to some of the models, Proxima is an M-class planet, which means it's a red dwarf, much smaller, much cooler than the sun. Proxima orbits very close to the star. Proxima B orbits very close to the star. And so we don't know if it's tidally locked, which means maybe, and also the red dwarf stars tend to be flary, which means they probably blow off the atmosphere of any planets around them, or if there's water, that gets blown out into space. So they've done some models, and if this is like science, right? They ask a question, what if this Proxima b had 10 times more water than Earth? Well, then over the course of its lifetime, there could be enough water to form an ocean, which is probably liquid on the sun side, the day side. So if it's tidally locked, there may be a liquid ocean. If there's a liquid ocean, there might be life, or life like we find on Earth. We don't know, but it just goes, it's the cool science. They're asking questions, they're trying to get answers using computer models and the best information. And I think that's kind of interesting to point out. Whether or not it could support life, we have to go there to see. So unless they're going to talk to us. We found a planet around a star that was predicted by Star Trek. How cool is that? 40 Area 98, you guys know that's Vulcan. This little planet is, let's see, our Eridani, 40 Eridani is 16 light years away. We can see it in the sky. It's in the constellation Eridanus, right? And so it's a super Earth. It's got a really boring name called HD 26965, which sounds pretty Star Trek. And, this star is just a bit redder than ours. It's just a little smaller, and it has a solar cycle much like ours, so of our suns. This star has a cycle of 10.1 years. Ours is 11.6 years. This is the sunspot cycle that we have. So kind of cool that science fiction is informing science in some ways, accidentally. Real quick, I just wanted to go through some of the Hubble images because the last one is actually a Saturn picture. But this one's NGC 4036, and 70 million light years in Ursa Major, so if we go out tonight, maybe we can find it. It's easily seen in these small telescopes, or larger telescopes. This was released as part of, just recently, they've been going through and doing these things. This is the subject that we're going to talk about, but this is part of the Coma cluster, which is a huge cluster of galaxies. You can see them all in that image. They're really drawn to the big elliptical galaxy in the center. That's the big gravity driver for the whole cluster. But what's cool about this other little spiral galaxy off to the side, it's a galaxy aggregate called NGC 4858. And what's cool is it's going nuts in star creation. So the red areas are hydrogen clouds where stars can be born. These blue areas are actually where new stars are being created. They call it a starburst type of thing. And it's got these luminous knots. And so they've been studying it because of just the galaxy formation, evolution part of the whole thing, which is pretty cool. And then, of course, Hubble's been looking at there's a new, they call it the Frontiers Fields and Legacy Observation, or Beyond Ultra Deep Frontier Fields and Legacy Observations. Buffalo, for short. Because NASA loves their little acronyms. So they want to expand the telescope's view into regions that are next to these big clusters. And if you see these little arcs here, those are galaxies that are on the other side of that area there. It's called gravity lensing. There's a big, massive galaxy there. It's actually bending light. And what they want to do is they use these gravity lenses as telescopes to see what's farther than this. These are beyond wherever these are. This field of view, this galaxy is much closer. Those tiny little galaxies, all those little dots in there are galaxies, not stars. This is a tiny little sliver of what the full moon. That's how tiny this little section of the sky that Hubble's looking at. And here's another one. This one's these are 41 massive galaxy clusters in that image. So they're looking for places for a James Webb telescope to look at when James Webb comes on, gets launched in a year or so. And then, of course, since we don't have Cassini anymore, Hubble took this image for you. So, pretty cool. And then I don't want to leave anybody out, but there's a thing called the Very Large Telescope. It's the most powerful telescope on Earth. It's down in Southern Observatory. It's part of the European Southern Observatory down in Chile. It's run by the Europeans, obviously, but sometimes the night's not looking good or whatever, so they get to point at other things. He took this picture just because it was cool to take a picture. So no real science here. What's neat about this is if you look right up here in this area, right there, there's a little streak, and it's in red, green, blue. They take the images in red, green, blue, and then combine them to create these beautiful images. This is an asteroid moving through, and so it moved when they took the red, or the red deal, the green deal, and the blue thing. So pretty neat. Actually, there's another one off screen that they didn't mention, but they mentioned that one. So kind of cool. It's just a beautiful image. Oh my gosh, I can't get over it. But closer to home, Judy and I went out a couple weeks ago. Judy, did you have fun?
Yeah, I had fun.
Can you stand up and everybody knows who Judy is?
Can you say, you want to talk about this?
Yeah. Talk about it.
Well, I have been an amateur photographer for 70 years. And finally it's starting to make sense, and so John's explaining to me, we'll do this. Mostly it was an issue of, can I trip over the tripod? Can I get the...
It was dark.
It was dark, and I only tripped over it once, and I said a word that John didn't know I knew. So we went up to the end of the road, and I asked him, he did. I explained it to him. So I have this theory that I am only going to take pictures. He offered to make them pretty for me, but no, this is just straight out of the camera. This is what happened.
You can do this too.
You can do this too.
I'm happy to, I invited several people out and only Judy could come, which is fine, but we can go out and have a star party of it.
It's a big parking lot.
End of Camping Road, right, at accident.
Yeah.
It is.
Mars, Saturn, or something. Saturn.
Jupiter's off to the right, but here's some more. More Mars. Looking towards Sagittarius, obviously to the south.
And so Judy, you did this, you were saying, 25 seconds?
Yeah, the first one that I did at our start party, I used 30 seconds, and I had trails. So 20 to 25 seconds, and 2,500 ISO?
Yeah, whatever.
Yeah.
I think you put it 24 or 25.
Yeah, something.
So there's a rule of 500 where, and this is just a guideline, usually it's 500 divided by the focal length of her lens. She was at 50 millimeter lens. Oh, that's the f-stop. And so she was taken to 10 to 15 seconds, and so it wasn't 50 millimeters, maybe 35. This is the big dipper, obviously. See the double star there in the handle. This is where we were.
You can actually, in the dark, read the sign.
Yeah.
That camera, I would see in the dark.
She really loved getting the plane trails, which were numerous that night.
I didn't know they were on there until now.
Now,
Yeah.
does it look better on the picture?
Yeah. And then I take pictures through the grass.
So, I've never heard Judy laugh with glee before. But really, this tickled her to death.
Yeah.
I took my flashlight and I held it just in my hand, so I just let out the tiniest bit of light to go past the grass. Well, it's open for looking at the other stuff.
UFOs off to the side.
Yeah, right.
Yeah. So do you have the one with the unknown in it?
Wow. I thought it was.
Oh, you did.
And this one, I'm sorry.
Yeah.
You can claim mine.
No, this one. Back one. That one. In between. Go forward one. No. In the direction. That one. No, this is a big difference.
Here's the square. No, this-
I'll
I've
find
been
it.
practicing all day to say, there it is.
These
Anyway, it was fun.
My magic status now is gone.
It's gone. It's gone.
So Judy likes to take pictures without any sort of, she doesn't like to process them at the image.
Right, that's why I have to
This-
be first.
yeah. So this is more real of what we see in the sky, but I've been using Photoshop
There it
for
is.
a long time. Look at that. There's the Andromeda Galaxy.
You just went by.
I just went by. This is the Andromeda Galaxy. I have a love affair with the northern Milky Way. And do you see the stone giant looking at Andromeda?
Big nose.
I was up at Mount Evans a month ago, or 10 weeks ago, when we were meeting before. I went up there with a friend. Well, no, this was during the Perseus, but I was up there that night too. This is the only Perseus picture I have ever gotten. Dang it! And look how far, it's all the way to the south. This is Mount Evans here, this is down at Summit Lake. Looking up Mars, looking almost straight up in the air. Obviously I like to bring out the color and brighten the whole thing. All I see in this image is Jurassic Park. This was the night I was with Judy, and Kathy must have put up this sign because it wasn't there last year. Which is fine. It is Axton Ranch. Hello, come on. More southern Milky Way. I'm not supposed to. We were having fun in the grass. This was up at 10 weeks ago when I was up there. This was at the Mount Goliath area. And I got to do a hike around there and find better spots because it was incredible. A car came and lit up this whole hillside and created that, man. It was awesome. And then this was when I was with Judy. That bright light is my cell phone, shining like this.
Space telescope, her focus is on moons in the solar system, including Earth's moon and those of Jupiter and Saturn. Why she's been asked, we were so delighted that she accepted, because we ran into each other on a book tour and actually debated about different places we want to go to. But she's co-authored a book called Beyond Earth, which is up back here, Our Path to a New Home in the Planets. She also got her PhD in aerospace engineering sciences from the University of Colorado in Boulder. And she's a great, she's got some new tasks. I mean, that was a good run. She's got new things she's doing, so it's never ending for her. And so give her a little attention here, and then we're going to go and break for the space station flyover. But we really appreciate you coming on.
Okay, well, thanks for having me.
Yeah, thank you.
Okay, so everybody know about the Cassini mission a little bit? Okay. Okay.
Not much, so maybe you can say a few.
Right, so I think people know, some people know some people know a lot, but I'll try to kind of cover all the bases. And as we go along, please feel free to interrupt me with questions. And if it's something that I plan to cover later on in the talk, I'll say, hold that thought. And hopefully we can have some good kind of discussion. Okay, so the Cassini-Huygens mission at Saturn. It was in orbit at Saturn until last year. The mission ended, sadly. But it arrived at Saturn in 2004, so it was there orbiting Saturn for a good 13 years. And I'll tell you some of the highlights of the mission and then about the grand finale, which is what we call the end of the mission, and some of the science that we learned during that end of mission. So this is one of NASA's flagship missions, meaning that it's a directed mission, it was run by JPL, and it's a big spacecraft. It was about as big as a school bus. About almost 7 meters tall, 12 instruments on the orbiter. And these are drawings from a couple of different angles that are pretty detailed. But the idea is that there's all sorts of instruments on here, 12 instruments. Here's the cameras. Here are thrusters that help us control not only attitude, well, mainly attitude, but we also use reaction wheels for controlling attitude. Forgive me if I talk in the present tense because I still haven't quite adjusted to past tense. And a big thing here is the antenna. This is the high gain antenna on one end of the spacecraft, and this is important because this is how the spacecraft talks to the Earth. And this is how we have to turn the spacecraft to Earth so that we can uplink commands and also so that we can downlink data. And so a lot of my job for a long time on the Cassini mission was planning out different sequences. And so I was doing icy moon flybys, and I'd plan out with a lot of people what we would do during these icy moon flybys, and which camera was going to take data when and how much data they got. And then we'd have to plan out, okay, now we need to turn the spacecraft back to Earth to downlink that data, and then uplink the next sequence so that for the next few days the spacecraft knows what to do. So that high gain antenna is important, and we'll come back to that too, because we use it for science also. So the spacecraft was launched, and I'm trying to keep an eye on the time, in 1997, and so it took 7 years to get out to Saturn, because it arrived in 2004, and it took kind of a long time because we wanted to not spend all of our money on getting a heavy spacecraft full of fuel off of the surface of the Earth. So we got some energy to get to the outer solar system by flying by planets in the inner solar system. We did 2 Venus flybys. So we launched in October 97 on this green trajectory, did a Venus flyby, did a second orbit around the sun, flew by Venus again, then flew by the Earth, and on each of those swing bys we gained energy to swing us out by Jupiter, and then finally arrived at Saturn 7 years later. And we did a lot of good science flying by Jupiter at the end of 2000, beginning of 2001. I mentioned the 12 instruments on the orbiter. And I call it the orbiter because the whole other part of the Cassini mission is the Huygens probe that we'll talk a little bit about too. But the orbiter is the main spacecraft that I showed you a picture of. We have the optical remote sensing instruments. Those are the cameras. And we had 4. We had the main camera covering mostly visible wavelengths. We had a near IR instrument, a far infrared instrument, and an ultraviolet instrument, and that's the one that I mainly worked on, and I still am because there's so much data. And then we had the MAPS instruments, and these are the magnetospheric and particle science instruments, and these are sensing electrons and ions and magnetic fields of all different energy ranges, and also measuring dust. And I'll mention the Cosmic Dust Analyzer, CDA, that gets lumped in with these in situ instruments. And then we have radar, and then RSS is the radio science subsystem, and that is basically that high gain antenna that I pointed out. So I'll tell you a little bit about some of the results from a lot of these instruments. Now I mentioned that we arrived in 2004. The original plan was to have a 4-year mission, where we're orbiting Saturn 74 times, and doing all sorts of unique science on each of those 74 orbits. And when we arrived at Saturn, Saturn has a tilt similar to Earth. So just like, we just went through an equinox, the autumnal equinox, because the Earth is tilted to the ecliptic by 23.4 degrees. Saturn is tilted similarly 26.7 degrees, I think. So when we arrived there in July of 2004, it was somewhere in the south in the Saturn system. And then Saturn's orbit around the sun is 29.5 Earth years. So we were just going to get a snippet of that year in our 4-year mission. But what we did was, at the end of our 4-year mission, everything was going great. And so we asked NASA for an extension. And we had a 2-year extended mission. And that was called the Equinox mission because then we saw Saturn go through equinox in August of 2009. And things were still going great, so then we got another extended mission, and we called that the Solstice mission, because that would allow us to stay until September of 2017, which would allow us to catch the northern hemisphere going through summer solstice. So we would see almost a whole half of the Saturn year by being there for 13 years. So this is really a fantastic opportunity. And really turned into a great thing where we could see seasonal variations of the planet and Titan, for instance. Or somebody cut me off when it's time to go outside. Okay. Now, I said I worked, for a lot of the time, I was at JPL, where basically all the operations of the mission happened. We did a lot of science planning and planning out what we were going to do to get all the science that we needed. And since it's such a big mission, we organized into 5 science areas. Titan, which is the big moon, and we'll talk more about Titan. The rest of the icy satellites, the rings, the planet, and the magnetospheric environment. And I'll focus on some of the results from the icy satellites area and the Titan area here in the next few slides.
So now, maybe we should.
Okay. Sounds good. Okay.
Yeah, we're just.
5 science areas to plan out this tour. And this is a graphic showing that initial tour that we planned out. The first 4 years of prime mission, and that was 74 Saturn orbits.
Dang it, get my
And so
specs
on
straight.
the
Sorry.
left-hand side is a graphic. If you're way up above the Saturn system looking down, those are all of the orbits. And this is in a coordinate system so that the sun is focused over on the right. And so the tour was designed specifically so that we get all sorts of all parts of the Saturn system from different lighting angles, different distances. We could look at the planet and look at the magnetospheric environment and all the rings and the moons, and be able to see them from different angles. Over here on the right is the same thing but shown from the side. So you can see that not only did we change the orbital distance and the angle with respect to the sun, but also the inclination with respect to the equatorial plane. And so this helps us get a different part of the magnetic environment and also be able to observe high latitudes on the planet, be able to observe the auroral zones, and also be able to look down on the rings. So a very carefully thought out tour, and the navigation team at JPL are experts in doing these kinds of plans.
How
Okay.
much are you perturbed in your orbits by the close passes to the satellites, to the
How much we
planets?
perturbed by the icy moons? Okay, Titan is significant, and lots of times we would fly by Titan not only to get science, but to get a little boost and be able to adjust the orbit for free. Titan's the second biggest moon in the solar system, and the biggest moon in the Saturn system, but all the rest of the moons are significantly smaller. So we would carefully track how much the trajectory was getting altered by them and know what they were doing to us, but it was not significant. Okay, good question. And if anybody has questions, don't hesitate to interrupt me. So this was the first 4 years, and then, as I said, we added on a couple more years, and then a few more years after that, and so the whole thing ended up looking like this. The final orbits that we'll talk about later are these green ones in here where we ended up getting it really close to the planet. So, okay, so let's talk a little bit about the system and the moons, which are my favorites. So Saturn has some 62 moons. As I said, the biggie is Titan, which is, the second biggest moon in the solar system, so larger than Earth's moon, but the rest of them are significantly smaller. But here's some of the main ones: Mimas, Enceladus, Tethys, Dione, Rhea, and then Titan. Those are kind of some of the main ones that we would focus on and do flybys of. Here they are and a lot of you have, somebody mentioned that they can see Titan easily and even Rhea from the ground, which is neat. But here they are kind of relative to the main rings and everything. Everybody knows the main rings of Saturn. Mimas, Enceladus, Tethys, Dione, Rhea. I don't expect anybody can see the E-ring from the ground, which is this broad, tenuous ring here. Reason it's probably hard to see from the ground is it's made up of very fine ice grains, we now know. And it actually extends from the outer edge of the main rings clear out past Rhea. But it's such fine grains that really you can't see them except when they're backlit. And so from Earth, it's hard to see. But we did do a lot of imaging of them, of that ring, of those grains, by getting the right lighting geometry with Cassini. But one of the questions going into this mission was always, where does the E-ring come from? It's so diffuse and broad that those fine rain particles, those fine water ice grains can't survive very long. So it must be continually sustained and produced, but what could be the source of it? It was known that the densest part of it is centered on Enceladus's orbit, and yet, model calculations that were done showing sputtering by micrometeoroids and plasma on the surface of Enceladus showed that sputtering wasn't enough to produce the E-ring and to keep it up. So that was always kind of a mystery of where that E-ring was sourced. Enceladus itself was an interesting target because we know already that it's the brightest object in the solar system. It has the highest albedo, and yet why that would be is unknown. So we planned out 3 flybys of Enceladus in those first 74 orbits, close flybys, to investigate that interesting moon. And we also planned several orbits of the big, several flybys of the big moon Titan. So here's kind of a schematic showing all of these flybys. So each column here is a year in the Saturn, in the Cassini mission. So there's 13 columns. This line right here shows you how many Enceladus flybys we did in that year. So there's 3 here total in the first prime mission, the first 4 years of the mission. And then after that, we added in a whole bunch more because we learned that Enceladus is really interesting. We also, these are all Titan orbits, so we planned a lot of Titan flybys. Again, because it's scientifically really interesting, but also because it's useful for, trajectory purposes.
How close is a flyby?
It varies. I think our closest Enceladus flyby was 25 kilometers.
Wow.
That's when we got really brave. But usually they're like 1,000 kilometers.
Yeah, right.
But what I mean by flyby really here is a targeted flyby. So we directed the trajectory and spent fuel if necessary to get to that point, to that aim point. There's lots of other flybys that are more distant that were still good for science. Okay. And then also this shows you kind of the season. By looking at Saturn, you can see, again, we arrived at summer in the south, and then we went through equinox in August of '09, and then we approached spring and summer in the north. Okay.
Did you observe any differences in of the planet when you're in those different seasons?
Mm-hmm. Yes. One of the things, and I wasn't going to talk about this, so I'm glad you brought it up, but did anybody hear about or see that big storm on Saturn?
Yeah.
That was really neat. That was a seasonal effect because there was this giant storm. You know what I'm talking about? It was a giant storm in the northern hemisphere, and it was called the serpent storm because it looked like a serpent head and then it ended up wrapping clear around the planet. And that was a seasonal effect. Just a change in temperature in the northern hemisphere. One of the things that you'll commonly see, and I'll just kind of describe it because I don't know if I have an image, but with the sun in the south, the parts of the northern hemisphere were always shadowed by the rings, and they're cooler. And then as that shadow goes away, things start to change in the atmosphere in the north. And what do I want to say? Other types of seasonal changes in the atmosphere probably triggered that storm. It's a type of a storm that happens every, I think I want to say 100 years or something like that. So pretty infrequently. So that was an example of a seasonal variation on Saturn. We saw temperature variations, and we saw seasonal changes on Titan too. And I'll tell you more about those when we get to the Titan part of the talk. But if I forget, ask me. Okay. Okay, so Enceladus, I've got a lot of people here know the story of Enceladus, but I'll go through it here. This is Enceladus as observed by Voyager in the early 80s. And so I already mentioned that Enceladus orbits Saturn at the densest part of the E-ring, and we know that it's the highest albedo object in the solar system. But we also knew that it was really interesting from Voyager because it isn't as cratered as it should be. So there's these areas that have craters, but it's not saturated with craters, like something that's sitting out in space for billions of years ought to be. And there's like these vast regions, at least at Voyager resolution, that appear to have no craters at all. And are even this kind of warped looking tectonic-like terrain. And it's a small body. It's only about 500 kilometers in diameter, so significantly smaller than Earth's moon. And it's icy. It's water ice rich, and it's small, and it's, you know, out at 9 or 10 AU from the sun. So why wouldn't it be heavily cratered? And why also wouldn't it be like coated in micrometeoroid dust, again from eons of orbiting out there? And so those are some of the questions, and we realized that the south polar area, this non-cratered area, looks like this from one of our initial flybys. And the South Pole, as you probably know, is like right there, and there are these giant fractures centered on the South Pole. And you know, it was this whole sort of dramatic thing on the Cassini mission, because we had these two flybys in February and March of 2005, close flybys, pretty close flybys. I mean, I think they were about 1,000 kilometers. And the magnetometer team said, on our next flyby in July of 2005, we've got to go a lot closer. We were planning on a 1,000-kilometer flyby, and they said, we think something is going on. We think that there might be some sort of a neutral cloud at the South Pole because Saturn's magnetic field lines are getting distorted, like there's an input of some gas or something from the South Polar region. And on the UVIS team, the ultraviolet imaging spectrograph team, we said, well, we don't think anything's going on because we had done this stellar occultation where we watched a star pass behind Enceladus, and if there was any atmosphere around it, we would have seen it. And instead, our signal looked like this, where we saw starlight, and then once that star hit the limb, it just dropped like a rock, because there was no atmosphere. And so we're like, magnetometer team, what are you guys talking about? But still, we changed that trajectory, and that was a big deal, because you know, we had the aim point at 1,000 kilometers, and then we changed it down to, I think, 75 kilometers. And then that had ripple effects for the next several months of the tour, so we had to change everything. But sure enough, we happened to have the stellar occultation on that July flyby right behind the South Pole, and we did sense that there was an atmosphere, like a local atmosphere, consistent with that plume. And on the same flyby, the other instruments also found that there's, you know, a plume at the South Pole. It was a few months later till we actually got images like this one, where you actually see the plume and you see the jets feeding the plume. But we knew as of July that there was water vapor and even organics coming out of the South Polar region there. So we now have an answer for why Enceladus has such a high albedo and what the source of the E-ring is, and it's this activity on Enceladus. So Enceladus feeds the E-ring, and that's why the E-ring is consistently present and Enceladus plume material coating the surface, and E-ring grains coating the surface with nearly pure water ice help keep it a very high albedo.
Is that like a geyser?
It's like a geyser,
So how
but
deep
it's
is it?
different from a
How
geyser.
deep is it coming from, you think?
Okay, I'm going to show you a cartoon in a second that shows us probably our best model of where it's coming from. But there was a lot of work that went into this because once we found this, we're like, oh my God, we gotta fly by this thing more and more, and get closer and closer. And so we found that there's always jets that feed the plume are coming right along those big fractures of the South Pole, and that's also where it's hot. So we know basically where it's hot, its material is coming out. And also, the CDA, the Cosmic Dust Analyzer, measured, and they measure by, kind of scooping up material as we fly through the plume and sensing what it's made out of. And they measure salts in these grains. And they measure that the salty grains, the bigger grains are saltier, and those are the ones that are closer to the surface. A lot of the salty grains don't make it out into the E-ring because they're kind of too big. The material that makes it out into the E-ring is the material that's in these super high-speed jets. So some of the salty material, salty grains do, but most of them fall back to the surface. But this is consistent with, an ocean source for this water, a salty ocean. And so this is the cartoon that I was talking about. So the idea that I think is a lot of people agree with is that there's this icy shell and there's a global ocean underneath the icy shell. So for a while there was some question about whether it was just a South Polar Sea or whether it was a global ocean. And now we have a lot of evidence that it's a global ocean. The ice shell is probably about 5 kilometers thick. And at the floor, it's a rocky ocean floor. So a lot like Earth. And we even know that there's probably hydrothermal vents, a lot like what's on Earth. Bringing heat and nutrients, potentially nutrients, at least minerals, into the ocean itself. And so this gets a lot of people excited, thinking maybe this ocean could host life. Maybe with the energy source, the proper chemistry, and the liquid water, those are the ingredients that we need for life, and so maybe this is a good place to go to look for life. And so a lot of people think about planning missions where we go fly through the plume, maybe multiple times, to scoop up material and look for dead bugs.
How about just a fishing pole with a hole in the ice?
So that was probably one of the neatest discoveries from Cassini. But a really other neat thing, of course, is the whole Titan story. And this, as a lot of you probably know, is what Titan looks like pretty much from the ground and also from Voyager. And it looks like a big orange ball, and that's because it's got a thick atmosphere. And it's the only moon in the solar system that has such an atmosphere. It's a very unique place. Mostly nitrogen, but about 1% methane and trace amounts of other stuff. But that now, as we know, this is the whole reason why we took a lot on the radar, right? Because you can't see through the atmosphere to see what the surface looks like with your eyes, with visible wavelengths. So you have to take infrared and also radar to be able to see what the surface looks like. And so now we know the surface looks like this. This is an infrared image, and we know that there's bright areas and dark areas, and it looks kind of Earth-like, although these are not continents. There are bright areas and dark areas, and we don't exactly know why. Compositional, textural change, variations across the surface. A lot of the dark areas we know are actually dunes. I think I have a slide later on showing you dunes. not sand dunes like here on Earth, but hydrocarbon dunes. Well, it's like hydrocarbon sand. And that atmosphere has got wind in it. So just like here on Earth, where the sand is blown into dunes by wind, there's wind on Titan enough to make dunes out of this hydrocarbon sand. Everything is kind of hydrocarbon rich. As a matter of fact, that's why the atmosphere, we can't see through it. It's smoggy and hazy because of large hydrocarbon molecules that are created by photochemistry of the methane, mainly in the atmosphere.
How warm is it down there?
It's cold. It's 90 Kelvin or so.
Okay.
I'll talk
So
more
it's
about
not a greenhouse effect, that atmosphere?
No.
Okay.
It's pretty it's pretty constant temperature. You know, on the surface, the temperature doesn't change too much because it is kind of insulating. I think I'll come back to that in a minute.
What is that Fahrenheit? Sorry.
Minus 276, I want to say.
Pretty chilly.
Find out, okay. 94 Kelvin. Okay. These are some new fancy false color images. These are from the VIMS, the Visual and Infrared Mapping Spectrograph. That just came out a couple months ago, showing all the variations on different hemispheres, which are neat. Okay, so I mentioned the Huygens probe. Here it is on the side of the spacecraft. This is in an environmental testing chamber at JPL, and here are some humans for scale in bunny suits. So, just to mention again how big the spacecraft is. But anyway, that's the probe on the side. Here it is, and this was a big contribution from the European Space Agency. And the probe was released at the end of 2004, and it was released so that it would go through the Titan atmosphere and land on the surface in January of 2005. And so here it is coming down through the atmosphere and landing on the surface. And it was not photographed by a Titan alien. It's just a cartoon, but we imagine it must have gone something like this. But this also gives you something of an idea of what it probably looks like on the surface of Titan. Everything's orangey, as I mentioned, because of all the hydrocarbon chemistry that goes on. Again, the methane in the atmosphere will tend to form haze particles after photochemistry, and everything will kind of accumulate and grow bigger and bigger haze particles and settle out on the surface. So even the surface is kind of orangey, not just the atmosphere. Although the atmosphere is not completely opaque. And so you can kind of see Saturn here. Of course, this is an artist's rendition, but it's not too far off from what it probably really is like. But you can see Saturn through the hazy atmosphere if you're on the right side of Titan, because it is phase locked. And it was predicted that Titan might have an ocean on its surface, a methane or ethane ocean covering the surface. And so the Huygens probe was designed so that it would survive whether it landed in liquid or a solid surface. And it turns out it landed on a solid surface, although evidently it was kind of damp. There's some evidence that it kind of bounced on kind of a spongy surface and then landed after a bounce and kind of was a little down. This is what it really looks like on the surface. I'm sure everybody's seen this image. Again, orangey atmosphere, orangey surface, hazy atmosphere, and kind of some pebbles and stones on the surface that are made of water ice, maybe a few centimeters across. And it brings to mind, to me anyway, because they look soft, like they've been eroded away by fluid processes. It looks kind of like river rocks here on Earth, like they've been deposited by some fluid action. So Earth-like in a lot of ways to me. Oh, here's the dunes, speaking of Earth-like. These are radar images of, at a couple of different scales of these dunes. They look like streaky features, but they are hydrocarbon dunes, and here they are compared with some dunes on Earth at similar scales, and you can see just how similar they are. So again, similar processes must have happened. What's interesting is that the Huygens probe, as it came down through the atmosphere, it did a lot of measurements of temperature, wind speed, wind direction, all that stuff. And it measured a lot of wind high in the atmosphere, like at tens of kilometers, and not so much low down. And I'll tell you in a second that we have other evidence for not that much wind at the surface, which is interesting, that the dunes maybe are thought to have formed episodically, like the pole. And here's kind of a map of the lakes and seas. There are some lakes, and at least A, C down in the South Pole, but there's more in the North Pole right now anyway. It seems like we've actually kind of thought that as the seasons change, we might see things changing more with the lakes and seas, and maybe more lakes accumulating in the south, but we didn't see that. So now we think it's more on a much longer cyclical time scale with those things. So we've got, what I was gonna say is about the wind. We have looked for waves on, especially the radar team has looked for waves on the lakes and seas, and really haven't seen any. And so the wind speeds are thought to be very low, at least now, and at least in the polar regions. So again, the actual whether or not dunes are being created right now is not clear. But those are at lower latitudes. Okay, so let me tie this to the book that I co-wrote that Leonard mentioned a little bit, because what we talk about in that book is Titan as a destination for humans in the future. And the main reason why it's attractive is because of the thick atmosphere. So the surface pressure is about 1.5 times what we have here on Earth. And I mentioned that it's very unique. In this book we were tasked to, we tasked ourselves with finding a realistic place in the solar system where humans might ever live for the long term. If there were a reason why we had to leave the Earth. And because of the really bad problems that are sourced by the dangerous radiation, especially from galactic cosmic rays, places that don't have atmospheres are hard, unless you want to live underground. And so Titan has this whole natural shield, which is the atmosphere, the thick atmosphere. And so humans could live there safely without having radiation problems. Now there's other issues, like how to get there, and it's cold. The cold is more doable. The gravity's low. It's a little, just similar to what we have on Earth's moon. But one of the neat things is that because there's a thick atmosphere and low gravity, you can fly. You can certainly take out airplanes or helicopters, but you can actually just fly by flapping your arms. You can strap on wings if you're getting lazy. And also you don't need a pressure suit because there's plenty of atmospheric pressure. All you need is a suit to keep warm.
And oxygen.
And you need oxygen, but there's plenty of water.
Right.
It's an icy moon. As a matter of fact, there's a lot of resources besides water. There's chemical resources, methano-type resources like in the lakes and seas. There's wind and even solar, even though it's far from the sun and there's a thick atmosphere. You can use solar. And there's stable surface liquids in case you want to go boating. So we actually wrote a paper that came out last year where we did a kind of a high-level look at some of these energy options and looked at how realistic could this actually be? And again, it was fairly high level, but we showed that some of these things are doable. And so I won't go into that in too much detail here, but I do have some slides in case anybody's interested after the talk. So again, not that, the main challenge is actually getting there, because if it takes you 7 years to get humans out there, they won't survive the radiation. And that's the whole reason for going to Titan. So you gotta find a quicker way to get there. But something to think about. Now, what I wanted to talk about next is the grand finale, the end of the mission. Okay, why do we want to do this? This was kind of how we like to think of this end of the mission, the last 40 or so orbits that we did, as a whole new mission, because we got in closer to the planet than ever before, and we like to call it like a little discovery mission. So we got to closer to Saturn than ever before, and why did we have to do it? Well, the main reason was because we were starting to run low on resources. Now, we could have technically left it in orbit around Saturn forever, and it would be in a pretty stable orbit. But there was a finite chance, even if it was very, very small, that we could crash into Enceladus, which maybe hosts life in its subsurface ocean, or Titan, which with all those organics maybe hosts some crazy sort of life. But also, I didn't mention, Titan has a subsurface ocean too. It's under a much thicker ice shell than Enceladus is, so we don't see evidence of it on the surface, although there's a chance it could access the surface. And if it does and it interacts with the organics on the surface, that's even more interesting maybe. But anyway, those are two astrobiologically interesting places in the Saturn system, and for planetary protection purposes, we wanted to not risk it, and we wanted to dispose of the spacecraft safely by depositing it into the planet. So that's what we did.
You mean crashing as opposed to depositing?
Sorry?
We use the word crash. Is that-
Crash, yeah. In doing so, we got very unique science. We were able to study Saturn's internal structure, the mass of the rings, and do in situ measurements of the radiation belts, upper atmosphere, and high resolution observation. Okay, I'll talk about a couple of those things. Here are those final orbits. Now we broke it up into two parts. We did first what we call the ring grazing orbits. And this is where we came in and we had periaps, the closest part of the orbit, just outside the main rings. And so that's already pretty close and pretty neat. We did, I think, about 20 of those orbits. And we came in, and these were kind of pretty high inclination, I think about 60 degrees inclination. And on each of those, we flew by Titan at the Apoapsis. And then we did the final set, the real grand finale orbits, and those are the blue ones. And on these, we decided to get really bold, and instead of going outside the main rings on periaps, we came inside the main rings and flew in between the rings and the top of the planet. And we did that about 20 times as well, 22 times, I think. And then on the last one of those, that was the final orbit. And then we actually went into the planet on that last orbit. So I think I have a little animation here for you. So here it is. Here they are. Those are those orbits. Yes, and I think this is going to show it to you from a couple of different angles so you can see what it looks like going in between the rings and the planet. And this was risky because, it doesn't look like there's anything in there. But it also doesn't look like there's anything in the Cassini division, right? But it's actually not free of material in the Cassini division. And we didn't know how free of material it was going to be in this region here. That innermost ring, the D ring, is very dark and hard to see, as you guys probably know. And so it's even kind of hard to tell where does that end. And who was talking about a paint chip, oh, this is the orbital debris thing, a paint chip going, what, 15,000 miles per hour?
17.
And so this, we're going 75, 80,000 miles per hour here at closest approach. So if there's a little ring grain in there, that's gonna nail us. So it's risky, but we did a lot of modeling and a lot of observing to try to make sure that area was clear.
What is that distance between the surface?
Here it is right here.
Oh, right
Here
here.
it is. At the top of this chart here is the D-ring, and that's at about 64,000 kilometers from the center of the planet. And then down here is 62,000 kilometers, so that's about 2,000 kilometers in there where we're aiming for. And that's from the center of Saturn. So, that purple dashed line up there is what we estimated was the inside of the D-ring. And then this orange dashed line here is where we wanted to not come below, or we'd be heading into the atmosphere. If we come down here, this is where we'll start to tumble. And we could start firing our thrusters to try to fight that tumble, but at some point it's not going to help, and we'll start tumbling out of control. So each of these columns is a flyby. So, and there should be about 22 of them. Oh yeah, 22. Okay. So on our first couple, we plan them out so they'd be well in between the two risky areas. We don't want to get too close to the D-ring. We don't want to get too close to the atmosphere. And they went fine. So on each orbit we were kind of like biting our nails, going, is this gonna work okay? And with each one it kept going okay. There was a couple of ones where we went out closer to the D-ring, and that was okay. And then on these later ones here, we came in closer and turned on the thrusters. Although it turns out that we didn't really need to. But we didn't exactly know what the Saturn atmosphere was going to be doing. We modeled it, but anyway, we had thrusters on, it went okay, and then finally on the last one here was where we went in, and that was the indication. Some of the science that we did was getting at the ring mass. Why do we want to get at the ring mass? Because this will give us an idea of how old the rings are and how long they've been around. There's a lot of people who think, well, the rings have probably been around since the planet's been around. But then there's people who think, well, why are they still so bright? Why aren't they darker then? Why haven't they accumulated more micrometeoroid dust? And why haven't they even evolved away? If they're old, they've got to be really massive. And there's some people who think, well, if they're young, then maybe, if they're less massive, then maybe they can be young, because otherwise they would have eroded away. Now, every time we fly by the planet on a normal orbit, we can get an estimate of the Saturn mass by sensing the amount of pull of the planet. But that's really the Saturn planet plus the rings, right? So when we fly in between the planet and the rings, then we're just really getting just the mass of the planet. We can subtract off the mass of the rings, and then we just get the mass of the rings. Does that make sense? Okay. So that's how we got the mass of the rings, by flying in between the planet and the rings. Before the ground finale orbits, our uncertainty in the mass was 100%. And Voyager told us that, the little moon minus, the rings are about 75% of the mass of minus. And we used 5 of our 22 passes to get the ring mass, just by orienting the spacecraft so that we could point the antenna at the Earth. Sometimes we wanted to do something else on one of those close passes, like take pictures of the rings, and so it wasn't as optimal for getting at ring mass. And now what we think is that the mass of the rings is something more like about 40% of the mass of Mimas, which is pretty low. And so that means that the rings are pretty young and probably under 100 million years old. And so I got this plot from somebody else, but the idea is that there were dinosaurs walking around on Earth when probably some interloper came by too close to Saturn and broke up and formed the rings. So pretty young. And maybe something a little bit more cyclical. Maybe it's unique. Maybe it just happens from time to time. Okay, a little more about the rings. There are 3 of the close-in rings that have actually been discovered by spacecraft. Pan, Atlas, and Daphnis were all discovered by Voyager or Cassini. And here they are. So Pan orbits in the Encke gap, Daphnis orbits in the Keeler gap, and Atlas is outside the main rings here. And what's really interesting, from these close-in orbits, when we could get good looks at these guys, is that they all have these skirts of material around their equatorial zones. Tutus, aprons, or whatever you want to call them. And what this probably is ring material. They're orbiting in basically next to or in the rings, but they're very small. I mean, you can see the scale bar here. Pan is some maybe 20 kilometers across or something, so they have very little gravity. So they're doing their best to hold on to this ring material around their middles, but not doing a very good job of it. Just barely holding on to it. But it makes them look like flying saucers, or maybe even some, oops, where did my little graphic go? I have a little ravioli graphic though, it's not showing. Sorry, the joke didn't work. Anyway, okay, so here's Daphnis, and you know that Daphnis and Pan Daphnis in the Keeler gap and Pan in the Encke gap, you know, they are the source of the gap. They clear out the material. And this is just, even though Daphnis, only 8 kilometers in diameter, it's very tiny. In this graphic, Saturn is up and Daphnis is moving this way. And you can see it creates these wakes of motion in the ring, in the outer edge of the ring. And you can maybe even see here that there's this like tail, very like little tendril of material that it has drawn out. Even though, again, it has very little gravity, but the ring material is affected by Pan only for a short time after it passes by. And this is actually also in the vertical direction as well, because there's a slight inclination in Daphnis's orbit, and so it affects the material both radially and horizontally and vertically. Okay. So, let's see. I'm getting close to the end here, but just wanted to share that Cassini imaged almost all the planets in the solar system, besides Saturn, of course. Except for Mercury, we got portraits of little points of light that are Mars, Venus, Jupiter's big, even Pluto, Earth and the Moon, Neptune, and Uranus, which is interesting also from kind of an exoplanet perspective. Because you can imagine that as we start to learn more about exoplanets, we can even learn more about planets in our own solar system, and also use what we know about planets in our own solar system to understand what might be happening in other solar systems. This is the final mosaic that was made of 42 images. mission ended on September 15th, 2017, and this was made on September 13th. So this is the final image mosaic saying farewell to the Saturn system. On that final orbit, some of my graphics aren't showing up here, I'm sorry. This just shows you the trajectory, and you've got Saturn in the background here. But in the last minute and a half, 60 seconds, you know, we were all kind of gathered at JPL and Caltech to witness, you know, the end of mission and the loss of signal, which happened. The spacecraft entered the atmosphere, and we lost contact when it was at about 9.5 degrees north, 53 degrees west. And the loss of signal happened at just about 5 a.m. Pacific. And again, the spacecraft was going about 70,000